oil degrading marine bacteria. And if those big names bother you, just think about that. Oil degrading marine bacteria. You don't have to worry about that Latin. It's found in low abundances in unpolluted environments in the upper layers of the ocean, but it quickly becomes the predominant microbe. Like 80 to 90% of the population in oil-contaminated open oceans and coastal waters where nitrogen and phosphorus are not limited. So this is a bacteria that lives there and is waiting for an oil spill, and then it will become the dominant species if it has enough nitrogen and phosphorus. What is the size of the black bar in the box? So what assumptions do we want to make? Like, we know most microbes are what size? It's about 2 microns if this is E. coli, but 1 to 5 microns is really reasonable, right? So how big is that bar if that bacteria is about 2 microns? The length, right? So these are like rod shaped, right? And they're typically 1 to 5 microns long. So that rod is about the length of some of those bacteria, right? That black bar represents about 1 bacteria. So how big is that? Which answer? What? 2,000. Yeah, it's about 2,000 nanometers because 1 nanometer versus 1 micrometer. Nanometer is 1 times 10 to the negative 9, and this is 1 times 10 to the negative 6. And so you have to move the decimal point over 3 spots. That one should be I typically try to make the first question easy. So you're like, okay, I got this. If it seems easy, that's okay. Don't stress. You're like, okay, got that. Okay, this next one is asking you to give a generation time. So remember, a generation time is the time it takes to have whatever population n and have it divide to 2 ways. So you could have a 1 going to 2, you could have 4 going to 8, whatever it is. You have some population and it divides. What type of scale does this graph have? That's right, it's like semi-log paper, right? But they're not showing all the lines because the y-axis has a log scale and the x-axis is just straight up. Is there more back there? There's one by Jess. Here's this. Give her that. You can take this one, okay? I'm going to try to grade that one. Don't be worried. Oh, Miguel's right there. Here, so what do you have to do to figure out if this is semi-log? Okay, so the bottom is 10 to the 5th, and then there's a line that you can't really see, and then this one it says 10 to the 7th, and this is 10 to the 9th. And I'm saying to use the closed diamonds. I went back and I looked because nobody came and picked up their final. If you want your final, you can always come pick it up, but I went and looked. Students saw this in 2 ways. One way was to look at the graph and assess where it started at. And most people said that this was probably, this starting thing, this diamond, was like, it's like 6 times 10 to the 5th or so. Like that was sort of the average estimate. People were trying to figure out like how high up this was, because remember on the log scale, the spacing changes, right? It's wider at the bottom, and then it gets more and more narrow as it goes up. And so the estimate there was about 6 here. Whatever you estimated, I was fine with whatever people estimated. It was close to that. And so if you're going to double 6 times 10 to the 5th, what value do you need to have? What is this times 2? 1.2 times 10 to the 5th, right? 6 10 to the 2 times this. Does everybody agree? 2 times that, what do you get? To the 10 to the 5th. The 5th is a, yeah. That's a tenfold increase. Goes from 10 to the 5th to 10 to the 6th. You only want to double it. If you're double. 1.2 times 10 to the 6, you'd be fine. Yeah, 12 times. 12 times 10 to the 5th, or 1.2 times 10 to the 6th? Yes. All right, so if we look at the graph, you would have to estimate that, and you can see here that there's a bit of a line. Where this ends up, right about here, maybe. I'm drawing it as well, so you are probably going to be able to draw it. This is at what, day 7. And so if you went here and you say, well, I think this is about 1.2, and then you come over, when I do that with a ruler, I get about a day. Does everybody get about a day when they do that? Right? So then you would say that the generation time is about 1 day. The other way students used to solve this is they said at day 0, so t equals 0, the number was 6 times 10 to the 5th. And then the next data point that's available is about 7 days on. So they said t equals 7 days. That's roughly, people get it down here, like 6 times 10 to the 7th. And then you can use the equation, solve for n, divide by the number of days. Does anybody want me to do that, or you prefer just looking at the graph? You prefer to use this. Okay, so let's look at how to do it this way. These are both perfectly acceptable ways to answer this. Okay, so remember the equations. N at time t equals n at time naught times 2 to the n, where n is the number of generations. And recall we're looking for the generation time, so once you have n, you still have another step. Okay, so nt is roughly 6 times 10 to the 7th, and naught is 6 times 10 to the 5th, times 2 to the n. So to solve this, you can divide both sides by 6 times 10 to the 5th. And then you would have 10 squared. The 6's are going to cancel. So you can say 10 squared equals 2 to the n. And remember, to get rid of the exponential, you can take a log function. So you can say, a little higher, you can see. So if we have 10 squared equals 2 to the n, we could say log of 10 squared equals n log of 2, and then divide both sides by log of 2, and we'll give you the number of generations. So how many generations? I got close to 7. It was like 6.7 or something. But Everybody else good about that? So you divide the number of generations by the time, and you get like a 0.9 something, which rounds up to about 1 day. Is everybody okay with both? Either way. You don't have to do both ways, but knowing one of these two ways. Yes, Andrea. I looked at the graph and I said, oh, this is roughly, I didn't draw it well on here, but if you look at your paper, I'm estimating that's at about 6 times 10 to the 7. Recognizing that this is semi-log paper, so that, remember, it gets wider and it gets narrower and narrower and narrower as it goes up. And it's just an estimate. I mean, we're just estimating this, so this graph doesn't have a lot of detail. So one significant digit is probably okay, say 1 day. We don't know exactly how many hours, but 1 day is fine. This next one should be easy too. This goes back to Appendix 1 and what you should know just about life in general. Give you a second to read it while I erase the board. Think about that. Thinking about nutrition of bacteria. So how can you explain the difference in this data? You've got the filled in stuff. Okay, so open circles is fertilizer, NPK is fertilizer. And open squares is oil spill, and the diamonds is pulled together. So it's the fertilizer and the oil. How can you explain that data? What?
Oil gives carbon, but it gives food source, right?
Yeah. Yeah, oil is providing carbon. Bacteria are carbon-based life forms. But the oil lacks some of the other nutrients, right? It doesn't have nitrogen, potassium, phosphorus. The other things that are necessary to make amino acids, nucleic acids, right? It can't do all that if it doesn't have those other nutrients around. And so that earlier paragraph where it says when there's an oil spill and there's other nutrition around, then the bacteria can grow well. So these people actually testing that out in a laboratory setting, saying, well, how do these bacteria grow with and without the other nutrition around? And so oil alone, it has the carbon, but it isn't able to do that. It's able to fix nitrogen, right? So obviously these bacteria cannot fix nitrogen. If they could fix nitrogen, then they wouldn't be reliant on the NPK as much, because most water will have a little bit of trace minerals in it. Not that interesting. Is that okay, Manuel? Looking okay. Like you're not like, well, that's not too bad, right?
Yeah.
Okay. All right, so turn the page. Use figure 1 to obtain a volume estimate of bacteria. Okay, so a cylinder, so you're going to approximate this is a cylinder. Volume of a cylinder is pi r squared L. And we decided, we've already got a length, right? We said it was about 2 microns, 2,000 nanometers. So L when I look at the picture, to me the radius looks like it's maybe a third of the length or so. What do you think? A third? How much? Fifth? What are people thinking? The radius is diameter. So if you're looking at one of those bacteria, and you're saying this is the length, you're trying to understand, like, estimate this size here. Like, maybe a fourth? So this is maybe like 4 of those to get. I'd say a fourth is reasonable. This person, on this one, they estimated it was a third, and that's fine. So that means that R, if it's a fourth of this, about a half micron.
Wait, that's the diameter. You're saying that the width is half of the bar.
Needs to be a quarter, I think, right? I think it's about a quarter of the bar.
So that should be 0.25.
If I divide this by 4, don't I get 0.5?
Yeah, I do. But are you talking about the diameter of the
I don't know what the radius, R? Oh, you're confused, Harley? Okay, so you're looking at figure 1. Right here. Figure 1 where you estimated the size in question 1. We decided it was about 2,000 nanometers long. So now we're trying to decide, can we estimate the radius? So do you think the radius is more like a half and the diameter is a quarter? Okay, so we'll say that. We'll say the diameter is a half. Does that make you all happier for your estimates? Which would mean the radius is a quarter. And so then you just have to put these into your equation. The volume is going to be pi r squared L. So we'll say pi 0.25 micrometers squared times 2 microns. What do you think, Troy? So this is pi. Put the square up there. 0.25 times 0.25 times 0.2. You could write it out. We said the diameter was a half. And so the radius is half the diameter.
Why is the diameter half? So that's fine.
So what do you think the diameter should be?
I think the radius is 0.5.
Yeah. I think that's a fourth of 2.
So if we look at the bacteria,
It's like 2 radius.
the whole length of this is 2 microns, right? So the whole thing is 1. So it looks to me like the diameter is about a half of that length, but I don't know. Do you think it's more like a quarter? If the diameter is the whole distance here to here. To me, the diameter looks close to 0.5. Let's just do Martha's rules. How many people want to go with 0.5 for the diameter? Thumbs up, 0.5? Okay. Don't care what diameter to use? Don't want to use 0.5. Okay, so most people are okay saying that the diameter is a half. Shannon,
So then when we're doing this on the exam, it's whatever.
you have to say my assumption is this. Like it depends on which one of those you look at too, right?
Just
They're
be
not all like
reasonable,
that.
right?
It's just an estimate, right? You're doing an estimate of the volume. So if you're in the ballpark, you'll be fine. If you told me that was 2 centimeters, I'd be like, no, not so good there. But it's okay, I think, to say it's a half, that the diameter is a half a centimeter. So this person used, they said it was a third of the length, which is a little long, but it's a little long. Maybe they look at it a different one. So you need to multiply this. What do we get? 3.4 times 0.25 microns times 0.25 microns times
0.39 microns cubed.
0.4
All right.
microns cubed. That's probably a better estimate with just one significant digit here, right? We're not like exactly sure like what the diameter is. And so that's not a good volume in terms of what we want to do though for fluid volume. So how would we convert that to like microliters?
We started. We spent.
Just could do it. I don't know if you.
Paying attention.
You have to do that 3 times. I don't know what your conversion happiness, where you find the best. Would you say centimeter is 10 to the negative 2 and micron is 10 to the negative 6? Or do you want to say there's, in 1 meter there's 100 centimeters, in 1 meter there's 1 times 10 to the 6 microns? Whatever, however you like to do your unit conversions, it's fine. But you must remember that this is cubed. And so you have to do this 3 times. If you're worried that you're not going to do it 3 times, then just write it out. You can just write this out. And now the microns should cancel out. We should have cubic centimeters, which is a milliliter. So micron, 1, 2, 3 goes away. And when I do these in my head, I just say, well, there's 2 here and 6 there. I get rid of those 2 and I make that a 4. Just do that. Do it on your calculator, I don't care. So this is 0.4 times 10 to the negative 12 cubic centimeters, which is milliliters, right? Looks like a close to half a femtoliter. Very small for one bacteria, but that seems reasonable. They're pretty small little things, right? You can plug it all into your calculator if you don't like to just do that cancellation. I like to get rid of all those big numbers right away. I don't like them hanging around. Does anybody put this in a calculator and agree or disagree with my number? Okay? Okay, just agree. Plug forward.
You are spending too much time on this.
Oh, this board is on the phone. We have new custodial staff. Let's see something that's not quite right. Try blue. Yeah, we don't see that over all the black smears. All right, so the Deepwater Horizon oil spill. I don't know if most of you heard about this big oil spill that happened down in yeah, the Deepwater Horizon oil spill. All right, so the Deepwater Horizon oil spill spilled 210 million gallons of crude. There are 3.8 liters in 1 gallon. So that's converted to gallon liters that way. crude oil is 87% carbon on the high end. Bacteria are 7.5% carbon roughly, for your book. What is the approximate carrying capacity of the oil spill? You're saying like if all of that crude oil got converted to biomass, how many bacteria could it support? Just like your cultures in the lab, right? Depending on how much you feed them, that's how much can grow. And how big the vat is at the brewery, that's how much beer they can make, whatever, right? So this is like a big batch culture where you've added 21 million gallons of crude oil. That's the nutrition source. So I did this, and then I have the clause there saying, well, the densities are going to be different. You know, obviously you have to cross-calculate, but let's just assume the density, the crude oil, the water, bacteria are similar enough with a rough estimate that we can just ignore the density differences. And so we could say that 0.87, 0.89, 0.87% carbon. This then would give us a rough estimate of the, if we want to, the liters of carbon, but we can convert it to kilograms if we want to. Tell me kilograms roughly of carbon. What do we get when we multiply this in? I got 6, 9. I don't know if you guys got this. The liters of carbon, roughly, if it was in a fluid. You too? You get 6.9? You got times 10 to the 8. 6.9 times 10 to the 8, right? I have too many significant digits right here, but we're not to the end of the problem. So it's okay. And then you're going to say, well, I have that bacteria. What is its volume and how much carbon does it need to be there? So we had 0.4 times 10 to the negative 12 milliliters of bacteria. Or I guess we could say 4 times 10 to the negative 11th if you'd rather. I don't know, whatever you like. And they're 7.5% carbon, so they are only 0.075. What are you scowling at me?
I'm just trying to read.
Is this okay? I think it's 0.4 times 10 to the negative 12 mils. We should convert because we have like liters there, so we could convert this to liters then. We could say that 1 liter is 1,000 milliliters. It's going to move this over to negative 15 basically. This will say how much carbon per bacteria, right? This will be liters of carbon per square. What do we get? What's the first number? 3 times 10 to the negative 17. Liters of carbon per bacteria. A rough estimate. So this is liters of carbon per spill. And we have liters of carbon per bacteria. And we want to know how many bacteria there are. So if we divide this below it, whenever you divide something, what?
I got 3 times 10 to the negative 14.
Milliliters, but then we converted it to liters. You do those? We want to have these be the same unit. Randy thought it'd be a good idea to convert. So we have liters of carbon and liters of carbon. So if we divide this liters of carbon in the oil spill by the liters of carbon bacteria, the spill is on the bottom, the bacteria is on the bottom, so the answer that you get is going to have bacteria per spill. And the liters of carbon are going to cancel. That's a lot of bacteria. What do we got? 2.3 times what? 2.3 times 10 to the 25th bacteria per spill. And everybody's answer on this was slightly different because everybody sort of estimated the volume slightly different. But it's okay. It should just want to be a really big number. Okay. Yes, Melissa. The last step is taking this and dividing it by that. So you take how much carbon you have in the spill and divide it by the amount of carbon you need per bacteria. And then the liters of carbon are going to cancel out and you're going to get bacteria per spill. Anything else on this? Just a crude estimate. Okay. The natural abundance. So the natural abundance is like how many bacteria are living there before the oil spill. It's 5.6 times 10 to the squared milliliters per milliliter of seawater. Then how long would it take to get to the steady state of 2 times 10 to the 8 CFUs per mil if the sea was contaminated with oil and the area was provided with the nutrients that it needed? Nitrogen, phosphorus. This again is a growth curve question. So you have a natural abundance of something, and then it's going to get to a high end. So we can use that equation.
Yeah, I got you. I don't know how I'm supposed to switch 30 minutes over. I was gonna do it on
So if you put this equation on your sheet, you might want to write NT equals N naught times 2 to the N. N is the number of generations, not a time. This is the most common error on this exam question every semester. That somebody thinks that once they solve for N, they have a time. N is the number of generations. It's not the time. All right, so NT is the steady state. Yes?
Could you write it in a darker color?
What can I do?
Could you write it in a darker color?
Sure. I was trying to avoid the black of everything else that was here. You could also move up a bit too. There's a lot of emphases.
Yeah, I can't see red, and I'm right here.
Okay, that's fine.
I can see it perfectly.
Okay, do you see that?
Yes.
Yes, okay. So the steady state, is that the time 0 or is that the time at time? Yeah, it's the NT, the number at the time. So we'll put 2 times 10 to the 8 CFUs per mil over here at time NT. It's going to equal time N naught, which is the natural abundance, 5.6 times 10 to 2 CFUs per mil, times 2 to the N, however many generations it's going to take. And so you divide this out, and then you use your log function again. How many generations do you get? take the log of this, divide this by the log of 2, and that will equal n. What do you got, Emmanuel? What number?
18.44.
So n is roughly 18 generations, right? So it's 18 days if you got a 1 in question 1. If you had a different value in question 1, exam I'm looking at, they estimated 2 days using the graph. And so they said, well, 18 generations is going to take 36 days. Whatever value you have, then you would take this generations and you would divide it by the we can multiply by the time for 1 generation, and that will give you the time. Well, we as a class decided the generation time was 1. So we would say 1 day, or 18 days, I'm sorry, right? Because it was 18, and our generation time was 1 day. The exam that I grabbed here, they estimated it was 2 days. So they said 2 days per generation, and their answer was 36 days. But that was consistent with what they got in question 2. So I was like, fine, you're being consistent, it's okay. Whatever value you think is appropriate. So they're not super fast growing, but they take over the niche, right? Because they're the only ones really that can use this one. So our book didn't really have this next question, but I went over it in class, so let's go over it here. I like this, maybe a batch culture, or a continuous culture. During the Deepwater Horizon oil spill, between 5,600 and 9,500 cubic meters per day of oil were spilled, using the full final volume of 21 million gallons spilled. What was the dilution rate per day? So dilution rate is the flow over the volume. So do we want to use the low end of the flow, the high end of the flow, or the average? Low? Okay, let's use the low end. So the low end is that there are F equals 5,600 meters cubed per day. And the volume that we have is in gallons. We did convert it to liters before, but then we took the 0.87. So I don't know if we need to do that one again. The volume, 21 million gallons times 3.8 liters per gallon. How do we get from liters to cubic meters? Do whatever you know, right? So if all you know is centimeters, that's what we're using. Like if you're really good, you can say, oh, a cubic meter is 10 centimeters, it's cubed, but that's fine. But if you don't know that, use what you know, right? Use what you know. Okay, so we can say that 1,000 milliliters, which is a liter, is 1,000 cubic centimeters, right, or centimeters cubed. No, yep. in meters cubed per day.
I thought liters was meters.
No, because a meter's like this big. So like if a meter cubed, we would have probably 1,000 meters, right? So it's 10 centimeters cubed, I think is a liter. If you do it that way, we're saying do what we know. We know 1 cc is 1 mil. Let's just go with what we know rather than trying to figure out something where we can't remember. All right?
1,000 milliliters over 1 liter.
We could do 1 liter. You're right.
Or yeah, you could do that too.
Let's do this.
Yeah.
Well, then I was going to have to deal with the liters and meters. So yeah, we can just do this one step in our head. That's super easy. 1 liter is 1,000 milliliters, 1,000 cc's. Now we have to get rid of this 3 times. So we can say that 1 meter is 100 centimeters, and we can cube it if you're comfortable doing that. But you can just write it out 3 times if you're not. Now you'll be in meters cubed. Gallons will cross out. Liters will cross out. And this has 1, 2, 3, and 1, 2, 3. So we now have an F. What is our V? Do I have a V? Does it come out to be? Does I have a number? Where it says whatever. You got it. Yeah. Does anybody have a balance? How many? What do you got? 7.10 times the meters cubed? Okay. So we're going to take our F. So we have 5,600 meters cubed per day. We're going to divide it by 7.9 times 10 to the 5th meters cubed. And our answer will be in per day, which is good. A dilution is always a per time. What is your D? A number. 0.007 per day. So the unit should then be day to the -1. So that's saying that 0.7% of that water is being replaced by oil during every day of that spill. Roughly 1% of the water is becoming oil.
Can you repeat the explanation of that number again? The water or oil?
So a 1, if this was a 1, 1 means that all of it was replaced in a day, or whatever per time you have. The dilution is all of it in that amount of time. In this case, we have 0.007 per day. So that's roughly 0.7% a day. Because 1/100th would be 0.01, and we're just below that, right? So it's close to 1% of the water is being contaminated with the oil per day in that area. They were just, well, this is like a range too, right? So it's kind of like it's coming out. They saw the oil coming out, and I think these are estimates. And that's why the range is pretty big, right? 5,600 to 9,500. You just see the oil gushing out, and of course you don't really want to admit that you're spilling oil. So hopefully you go with the lower breath estimate. The image This one here? Yes. This was a cubic centimeter, so 1,000 milliliters in a liter. 1,000 cubic centimeters is 1,000 milliliters per liter. We could do it multiple steps, but we decided we just say, we know a cc is a mil. So what type of metabolism is being shown in the next step, where it's malonyl-CoA, and then that malonyl-CoA decarboxylase is creating carbon dioxide and acetyl-CoA. What do you see there? Fermentation, right? That's fermentation. It's degrading, it's catabolic. The broad category here is fermentation. What's wrong, Julio? Arm? Number 8?
This is a lot of math.
This one's not math, it's just fermentation.
No, I got that, yeah.
Okay. Life is a lot of math. I'm just trying to decide which colors I use and I'll be able to see. So, it's saying to redraw the image, fixing the errors, and showing a more complete metabolism. So we talked about fermentation being, red doesn't work, purple. So we talked about fermentation being a two-step process. You'll see this in your own liver, fat metabolism. If you want to do it more human physiology or animal physiology. There's a small molecule or a smaller molecule with coenzyme A, and there's a transfer. There's some enzyme, some transferase. It's going to be here. It's a X transferase. And the coenzyme A is transferred to the bigger molecule. And then there's some sort of cleavage reaction. Something's being cut off. The one here is a decarboxylation, so it's a decarboxylase. And so you just see that this thing gets cut off here. The cleavage happens, and you end up with new substrate. And so the overall reaction, when you have these two half reactions together, is simply X, Y goes to X and carbon dioxide. But that really doesn't show you the full elegance of fermentation and how this product of reaction 1 is becoming the substrate of reaction of 1 in reaction 2. And therefore, because of delta G naught plus RTLNQ, you're taking away the product, converting it back to a substrate, and it becomes super catalytic. And so all we would need to write for this then is that we need to have The smaller one, which of these two will be smaller, acetyl-CoA or malonyl-CoA? Acetyl-CoA. So you would put the acetyl-CoA here, plus malonate, or malonyl, and then you'll get acetate, plus malonyl-CoA, and then it gets decarboxylated and you get the acetyl-CoA. Try to write that. I'm gonna have you try to write that, but try to erase something. Most books I have found do not do a great definition of fermentation. They say it's an anaerobic process that's lower energy. It causes gaseous evolution of different gases. So this gas could be methane, it could be nitrogen, it could be ammonia, it could be ethanol. But every time I've gone to the literature and tried to understand the molecular mechanism, it looks like this. Some organic substrate is put in there. So it's like you're taking an organic compound and you're breaking it down. You're catabolizing it using acetyl-CoA rather than like going to the electron transfer chain with NADH, right? Or the oxygenic, like respiration. Andrea? They all have the same general feature where it's like a smaller molecule with a CoA. All of them do, right? So this is a small molecule, and then it's something that looks like a small molecule but has another part to it. This small molecule could be, like this could be, the Y could be ethanol, and that could be an X. It could be like propionic acid or something, right? Is everybody else okay with this except Andrea? Does anybody want me to write more on this? Sure, great enough. I'm so frustrated by this chalkboard. I can't even tell you. It's like, what? Actually wipe it? Yeah. Wonderful. You might be able to see it. What? What do you want? I'm going to write it out. That's why I'm trying to get this spot where I can actually read it. So that's one of the problems here is this carbon has 5 bonds to it. Many people notice that on the exam. O minus, I don't care if you do OH or O minus. You start off with the smaller compound, the acetyl-CoA, get the larger compound, the malonate. They will combine, so there's going to be a transfer to red. So you will end up with what 2 things if you transfer that? Acetic acid. Yeah. And malonyl-CoA. So you'll have this compound, but it will have the CoA. So I'm going to draw it here, a bit cleaner. Where's the cleanest spot? Right here. So this is the malonyl CoA. This CoA has been transferred from the acetate to the malonate, and it's now over here, been added here. You also will then have the acetate. Acetic acid, acetate, malonyl CoA. And then the second step is a cleavage reaction. We're going to cut off carbon dioxide. So that gets cut here. Big enough to see in the back. And you'll end back up with acetyl CoA, and then the carbon dioxide will come off. So the overall reaction in almost every textbook is simply this magically goes to carbon dioxide and this other smaller thing. But the details of it are that it's super energetically favorable because you're coupling these two reactions together, and this one is creating more substrate for the first one. The next one should be pretty easy. It's simply looking at the flat end and the pointed ends of the arrows and saying, okay, what is reaction in there? Wait, what? What's what you know? Just CO2 coming out. I'll erase somewhere else. Erase somewhere else. It's really working there. We still waiting? If I do it now, will somebody wait? Okay. It seems like this part of the board is slowly getting better. Whatever compound they put on here is being better. I'll try that. Thank you.
Mark is red.
Picky on the man.
Alright. Alright, so all the substrates only have a flat end of an arrow, so we have alkane and oxygen, NADH, H plus. This is going to water and aldehyde and NAD+. That's all that one required. What is the reaction? It's really hard for me to evaluate the next question if I don't know what reaction you're looking at. What is the change in standard reduction potential for the reaction? You just ignore that alkane aldehyde redox stuff. We're just going to worry about the oxygen, water, and then NADH and NAD+. Which one looks like the standard reduction potential table? Right, so we'll put the oxygen one here, 0.816 volts minus negative 0.320 volts. And that should be 1.136 volts, but it's only got 3 sig figs, so 1.14 volts. The overall standard free energy change for this reaction when the alkane and aldehyde redox couple is negative 91 kilojoules per mole. And what is E naught of the alkane aldehyde redox couple? How do we solve that? What I would do is I would figure out what is delta G for this. We know the overall, we can subtract it, we can say what is the other one contributing. Yes?
Can you explain why you're not flipping the second one?
I am. There's a negative sign here that is flipping the sign, because this one looks like the table, and I'm subtracting the one that doesn't look like the table.
Oh, so you could.
You wouldn't use this equation if you're going to do that then, because you don't want a negative and then flip it.
No, I would put positive.
Yeah, you can just say this plus that. Yes, that's what this is doing.
Yeah, that's what we do.
Alright, so delta G for this part of the reaction is negative N, and what is N? 2, negative N, 96.48 kilojoules per volt mole times delta E, which is 1.14 volts. We know it's 2 because when you look at the standard reduction potential table, it says 2 electrons are added to oxygen to make water. And you can see that 2 electrons come off of NADH, right, to get to NAD+. Those are going to the oxygen. So 2, this is the number of electrons transferred. Not the total in sum. It's like how many started here and ended up over there. And so it's the number transferred is 2. 2 leave NADH and go to oxygen. What? So we have a number for this. Train, you have a number? Oh, not yet. Negative 220? Kilojoules per mole? Okay. So if the overall reaction is negative 91, remember when you have reactions that are there, they can be additive. So the delta G of this and that together make that. So we have negative 91 equals negative 220, and then whatever the delta G is for the alkane halide. So it's going to have to be a positive number, right? Positive 1. We have to undo what we just did with the delta E and G. So we can say that this delta G equals negative 2 times 96.48 kilojoules per 6, 7. Okay? Seems reasonable looking at those numbers? Question 13 is about cyberpores. Remember, cyberpores are molecules bacteria spew out into the world with the hopes of getting something back. Like, they can get iron. In this case, these bacteria aren't getting iron, they're getting oil, right? So they have a cyberpore that's leaving their cell to try to scavenge oil and then bring it back. So it releases an anionic biosurfactant type of cyberpore. It's able to assist in the uptake of oil. How does it work? What is that cyberpore acting as? What is it doing? Use it in the lab every time before you leave. Soap. It's acting like a soap. It's like a detergent, right? It's actually making a micelle around the oil so that it can get it out of the water and have it kind of captured. And then it brings it back to its cell and it says, I can have this oil now. So this cyberpore has those long polar chains on it and it looks like soap. It's as simple as that. That's all you have to say. It's a lipid. The oil is a lipid. This cyberpore is able to get the lipid, right? You know, in an oil spill, the oil is just going to be sitting on top of the water. It doesn't want to mix with the water. And so this is actually helping get it into where the bacteria want it to be. It's like making a detergent and saying, I'm going to get that oil for myself. The next picture shows you some of the details of an experiment people did trying to understand how this works. At the bottom, they're saying, okay, I truncated you. Sorry, it saved like 100 sheets of paper. I crammed it all together. So there's an oil droplet. Let's see if I can draw this. To break up the oil spill, disperse the oil spill. And there's 3 types of dispersants that were studied in this experiment. There was a non-ionic, just sort of up there at the top. And then there's an amphiphilic surfactant here in the middle. And then there's this anionic one down here, which means there's anions on it, negative charges. So if this cyberpore, the bacteria, so those are the dots that are out here. These dots out here are the cyberpores of the bacteria. They are trying to get to the oil spill and capture some of it for themselves and bring it back. So what they found is that these different dispersants that they have interact with the oil spill. And what they do is they're adding like a casing around the oil spill that has, there's charges on it here, the ones that's anionic or the amphiphilic. In the case of the non-ionic one though, it's just adding an extra layer of non-polar stuff around the oil. So you have here, you have a layer of non-polar casing, penestrine oil droplet. Here, you've got a layer of this amphipathic molecule that's allowing the oil to be in solution better, but it's still interacting with the oil, right? The nonpolar part of this is interacting with the oil and causing it to be surrounded. And in this case, the anionic one, it does it really well, right? It interacts and doesn't. How is that going to affect the cypher-4's ability to get to the oil? Is it going to help it or hurt it? Will be no difference. It's going to hurt it. So in this case, it's like the dispersant is sequestering or taking the oil, it's like out-competing the bacteria for the oil. So instead of letting the oil, the cypher-4 and the bacteria get to the oil, we're adding compounds to the oil to make it interact with the water, but then it's cased away from where the bacteria would like it to be so they can use it. Most people had a really hard time with this question last spring. I don't know. I think the picture wasn't very good. Most people said, yeah, that's helping the bacteria in some way. The last question was more policy related, so again, no math again. It's just like, okay, do you think this is good or bad? And as long as the person was consistent with the previous one going to this one, I was okay. So in this case, this is from this National Resource Council Oil Spill Committee. And they're like trying to understand like how great these dispersants are. And they're saying, if we have dispersion, then it's going to help these bacteria, and then it's going to all go away.
That's how Exxon got away with Exxon.
Yeah.
The government wouldn't let them use dispersants.
Yeah.
And Exxon let them.
And then the bacteria ate it. Yeah. They also did build a really nice aquarium up in Alaska. I brought my girls' coach. Great.
Yeah, it's actually flexible.
Not yet.
You
Believe
would
it.
think
So, and I was saying that Rex Tillerson was the head chemical engineer of Exxon at the time of the Exxon spill. Yeah. So I don't know, like these policy questions are really dicey, right? Like what data do you use? Do you say, oh, we don't want the oil spill to be there, it looks really bad for tourism, it's not really great? Or do you say, well, there's actually some bacteria there that we could promote that might want to eat the oil? What I would really like to do now, I know about this FTIR that can pick up this synthetic compound years later. We kind of want to go to where there's been an oil spill and they've used dispersants and say, is that synthetic compound still there?
What about seeds?
Yeah.
Well, there's like
There are natural seeps all the time, there's oils, and I think that's why these bacteria exist in the world, because there are natural seeps of oil. Oil is not an artificial ingredient, it is something that was made naturally. But the dispersants might not be natural.